Hello guys, this is the last part of electrophilic addition reaction in which we are going to discuss the electrophilic addition reaction across the carbon triple bond carbon, that is in case of alkyne. And these addition reactions are addition of halogen, hydrogen, addition of hydrogen halide, addition of water. In addition to this, we will see one substitution reaction of alkyne. It is nothing but the formation of metal acetylides. The reactivity of alkyne and how it undergoing a electrophilic addition reaction, that we have studied in the first video on the electrophilic addition reaction, and the mechanism of this halogen, hydrogenation, hydrohalogenation and hydration, that we have studied in the electrophilic addition reaction part 2nd, 3rd and 4th. So in this video we will focus only on the chemical reaction. We will not going through the mechanism of this reaction because they have already studied. Now see the first two reaction, that is addition of halogen and hydrogen. Here halogen and hydrogen, they are symmetrical reagents. Therefore here just there is an addition of halogen or hydrogen across the triple bond, so no Markovnikov rule is there. But in case of addition of hydrogen halide and addition of water, as the electrophilic reagents are unsymmetrical one, therefore in case of unsymmetrical alkyne we will see a Markovnikov addition, and in the formation of metal acetylides we will see the acidic character of hydrogen which is present in the alkyne. So let's start with the first reaction, that is addition of halogen. Addition of halogen, which is also called as a halogenation. See here, ethyne, that is CH triple bond CH, when it undergoes a halogenation, that is with the chlorine, it will form a trans 1,2-dichloroethene. Why trans? Because we know that there is a formation of halonium ion, and that halonium ion, it is attacked by the nucleophile, that is Cl minus, and anti-addition is there. So here we get the trans product. Just one Cl is going to attach on this carbon and another Cl is going to attach on this carbon in the anti manner. That's why we get a trans 1,2-dichloroethene. Alkyne is converted into the alkene in the first step, and in the next step another molecule of the chlorine will going to have a reaction with the alkene and it will form a corresponding alkane, that is tetrachloroethane. Here also this Cl2 will have a anti-addition across the double bond, so that here we get 1,1,2,2 tetrachloroethane. So from this reaction it is clear that just we have to add a Cl2 molecule across the carbon triple bond carbon. Similarly, propyne, it will react with the Br2. First step is the anti-addition of Br. Here we get a propene, that is the alkene. In the second step, another molecule is going to add here and we get a tetrabromopropane, 1,1,2,2 tetrabromopropane. So this reaction involves the halonium ion and the anti-addition of either chlorine or a bromine. Now we will see the second addition reaction, that is addition of hydrogen. As like the addition of halogen, hydrogen also shows a hydrogenation reaction when it is heated in presence of metal catalyst along with the alkyne. This is the first reaction. Ethyne, when it treated with the hydrogen in presence of a metal catalyst, it gives ethene. There is the addition of two hydrogen across this triple bond. Then in the second step, this ethene also shows a hydrogenation and it gives ethane. So alkyne is converted into the corresponding alkane by the addition of a 4 hydrogen, that is 2 molecules of the hydrogen. Then in case of propyne, similar reaction is there. In presence of metal catalyst, this hydrogen will attach to these carbons so that we get here a propene, and then propene is converted into the propane. So I will write here one hydrogen, it will attach here, another hydrogen, it will attach to this carbon, we get a propene. In the next step, it will attach to this carbon, second hydrogen, it will attach to this carbon, so that we get here a propane. In this way, addition of hydrogen or hydrogenation reaction take place. Now, the third addition reaction, which is nothing but the addition of hydrogen halide, or which is also called as a hydrohalogenation. In case of addition of hydrogen halide or hydrohalogenation process of the alkyne, we have to consider a Markovnikov rule, because this hydrogen halide, it is the unsymmetrical electrophilic reagent. See the first reaction, ethyne reacts with the HBr. Here ethyne, it is a symmetrical alkyne, therefore here we cannot apply the Markovnikov rule. But in case of propyne, we have to apply the Markovnikov rule. Now see the first reaction. Ethyne when reacts with the HBr, this hydrogen, it may attach to this carbon or this carbon. Then we get here a phenyl bromide. A Br is going to attach, and this triple bond is converted into the double bond. So that here we get a CH2CHBr, which is called as a phenyl bromide. Now, in the second step here, this phenyl bromide, it is a unsymmetrical alkene. Here there is a CH2, here there is a CH. So that when HBr is going to add this hydrogen, it will attach to this carbon, because this carbon has two hydrogen. This carbon has only one hydrogen. And according to the Markovnikov rule, the positive part is going to attach to the carbon which is having more number of hydrogen. So that here we get a CH3, CHBr2, that is 1,1 dibromoethane. So interesting thing is here, Br, that is here HBr and here HBr, two Br atoms, they are attached to the same carbon atom when there is a addition of hydrogen halide across the alkyne. So here we see CH3CHBr2, 1,1 dibromoethane. Let's see the second, a propyne. Already it is a unsymmetrical, and HBr is also unsymmetrical. So in the first step, there is a Markovnikov addition. Here we get a H is going to attach to this carbon because it possesses hydrogen. Here there is no hydrogen. So that we get CH3CBr double bond CH2. Again, this is the unsymmetrical. And in this step also, it will attach to this carbon, and Br, it will attach to this carbon. And here we get 2,2-dibromopropane. CH3CCH3Br. So in case of ethyne, first step is a normal product, no Markovnikov addition, but in the second step we have to apply the Markovnikov addition. And in propyne, from first step we have to apply the Markovnikov addition. But the products here and here, on the one carbon there is a presence of two halogens. So in both cases we get a product which is having carbon attached to the two halogen atoms. This is the hydrohalogenation of alkyne. Now we will see the fourth reaction, that is addition of water molecule, that is called as a hydration. Addition of water, it is the hydration process. We know that in the addition of halogen, in the addition of hydrogen, or in addition of hydrogen halide, we have studied that there is an addition of two molecules of electrophilic reagent. But in case of addition of water, there is an addition of only one molecule of water. So this is the major difference between the other electrophilic reactions and addition of water. Only one molecule is going to add across the alkyne, but in presence of mercuric sulfate and H2SO4. In case of alkene, we have studied the hydration reaction where we are using H2SO4, dilute H2SO4. But in case of alkyne, we are using here HgSO4, which is dissolved in the H2SO4. Why it is so? Why we are using here mercuric sulfate. The main reason behind this is alkynes are less reactive as compared to the alkane. Therefore, to increase the rate of reaction, mercuric sulfate is used. So, when alkyne is treated with the water in presence of this combination, that is HgSO4 dissolved in the H2SO4, we get addition of OH and H across this triple bond. So H is going to add here, and OH it will going to add at this carbon. This triple bond is converted into the double bond, and here we get ethine is converted into the alcohol, but this alcohol possesses a double bond, and to this doubly bonded carbon there is an attachment of OH group. It is the enol form. It is the enol form of alcohol, or it is also known as a vinyl alcohol in case of this compound. Then this enol form it will convert into the corresponding keto form by a keto enol tautomerism, in which this OH bond it will broken down and the electron they are shifted on this carbon oxygen bond. There is a formation of carbon double bond oxygen, and this hydrogen which is H plus now, then there is a shifting of this pi bond on this carbon, so carbon becomes negatively charged. It will abstract this H plus ion, so there is a transfer of this hydrogen from the oxygen to the carbon, and we get here a CH3CHO, that is acetaldehyde. It is called as a keto enol tautomerism. So when one molecule of water is added to the ethine, we get vinyl alcohol, which is undergoing a rearrangement or keto-enol tautomerism, and here we get a acetaldehyde. Similar strategy is used in the propyne as well as in a butane. See the propyne. Here propyne, it is an unsymmetrical alkyne. So we have to consider a Markovnikov addition. When hydrogen and OH they are going to add across this triple bond, the hydrogen which is a positive part it will attach to this carbon, whereas OH it will attach to this carbon. So here you can see COH double bond CH2. This is the enol form of the alcohol. Then it will shift the electron here, then it will shift the electron on the carbon. This hydrogen it will transfer from this oxygen to this carbon, and we get here keto enol tautomerism. Enol form is converted into the acetone CH3CO CH3. Similarly, in case of butane, it is the symmetrical alkyne, so no Markovnikov addition. Just we have to add hydrogen and OH according to our convenience. So H is added here, OH is there. It is the enol form, then it is converted into the keto form, and here we get a 2-butanol. So in case of addition of water, the only one molecule of water is added across the alkyne, and we get a enol form in the first step, which is rearranged via keto-enol tautomerism to the corresponding carbonyl compound. It may be a aldehyde or a ketone, which depends upon the structure of alkyne which is taken in the addition of water. So these are the electrophilic addition reactions of alkyne. Now we will see the substitution reaction of alkyne. Formation of metal acetylides. It is the substitution reaction of alkyne, where the hydrogen is replaced by the metals. Why they are replaced or how it is possible? To understand this concept, we have to consider the structure of alkyne. It is the ethine, and its structure is written here once again. See the structure. The carbon they are joined by the triple bond. This carbon they are having a sp hybridization, and in sp hybridization, this sp hybrid orbital axially overlap with the 1s orbital of the hydrogen, and it forms a carbon sigma bond hydrogen. Similarly, on this side there is a formation of carbon single bond hydrogen. It is the sigma bond by the axial overlap of sp hybrid orbital of the carbon and 1s orbital of the hydrogen. Now we know that sp3 hybridization, then sp2 hybridization, and sp hybridization. In case of sp3 hybridization, The percentage of S characters, they are 25. In this, S characters are 30%, 33%. In sp hybridization, the S characters are 50%. Now, here there is a sp hybridization. That's why the S character of these carbons, they are more. It means that the increase in S character increases the ability of carbon to attract the electron towards itself. It means that the electron in this bond, they are attracted to the carbon, or carbon attract this electron towards itself due to the more S character. That's why the carbon hydrogen bond, it is weaker one. It is the weak one or weaker. And this hydrogen, it can be removed easily when the alkyne is treated with the metal. In this way, alkyne is having acidic hydrogen. Now see the reactions. First reaction, it is the formation of sodium alkynides. When alkyne is treated with the sodium in presence of liquid ammonia, then the hydrogen which are present, they are replaced by the sodium and we get here salt. Similarly, this alkyne, when it is treated with the liquid ammonia, we get a corresponding salt. Instead of sodium and liquid ammonia, we can directly use a sodamide, that is NaNH2. It will causes the replacement of one hydrogen of the alkyne and we get a corresponding salt that is called as a sodium alkynides. It is due to the acidic nature of this hydrogen. Now see the second reaction. This alkyne, they reacts with the heavy metals such as copper as well as silver, and they forms the corresponding alkynides. Acetylene treated with the ammoniacal solution of cuprous salt, that is cuprous chloride is dissolved in the ammonia and it is treated with the acetylene. Then there is a replacement of hydrogen by a copper and we get here copper acetylides and it is having a red color. Similarly, when acetylene is treated with the ammoniacal solution of silver nitrate, it means that silver nitrate is dissolved in the ammonia and it is treated with the acetylene. Once again, the replacement of hydrogen is taken place by the silver and we get a silver acetylides which is having a white color. In this way, a metal can be used for the replacement of hydrogen, and when these metal solutions, they are treated with the alkyne, the hydrogen is replaced by the metals and we get sodium alkynides as well as copper alkynides or silver alkynides, which is having a different color. This is the substitution reaction and it clearly indicates the acidic nature of alkyne. So in this video, we have gone through the details about the alkyne, its electrophilic addition reaction and substitution reaction. So with this, we will stop here.